This is Jim Pennington. I'm a chemistry professor at Texas A&M University. I'm an associate instructional professor. I'm also the coordinator for the Texas A&M Chemistry Roadshow, and I'm happy to welcome you here to our presentation at the George Bush Presidential Library today. We do this presentation all over the state of Texas. We do about 80 or 90 presentations a year, so if you're in Texas and would like to have us come to your location, please contact us and we'll be interested in setting that up. Today's program is sponsored by the George and Barbara Bush Foundation. It's made possible by the Education Department of the George H.W. Bush Presidential Library and Museum. We appreciate all the support, both financial and physical and human support that we've been given for that. President and Mrs. Bush advocated support for scientific research, specifically cancer research, throughout their adult lives, having lost their young daughter Robin to leukemia at an early age. Their advocacy for research has led to cures for many childhood cancers and has saved the lives of many children and advanced that research progress, and we're grateful for that. In addition to today's specific sponsors, the program is also sponsored by the Texas A&M Chemistry Department, the College of Science, as well as grants from Shell Oil and Dow Chemical. We very, very much appreciate that support. Whenever I do these presentations, I think it's also important to be grateful to people who went ahead of us, who laid the groundwork for things. This Chemistry Roadshow was originally started about 30 years ago by Dr. John Hogg. He passed away about 12 years ago, and I took over the presentation when he passed, but I'll mention him a couple times as we go throughout the presentation. Now, as I said, we go all over the state of Texas doing this show. Lots of places we go. We'll call this a chemistry magic show. People like the idea of magic. With magic, you don't actually have to do any work. You're just gonna pop the top off the bottle, and the genie comes out and just does all the work for you. Not bad, we got a pretty decent genie going today. Fortunately, no genie. Lots of heat, lots of steam, very exothermic reaction, but no genie. Part of our purpose in doing this presentation is to help you guys remember that all that hard work you do in school, the reading, the writing, the math, the science, will actually let you do some pretty cool, some pretty interesting things as you grow up and as you go on in your academic career, and we hope to show you some of that stuff today. Now, like I said, lots of people call this a chemistry magic show, so I guess I should put on the uniform. Dr. Hogg hated when people called this a chemistry magic show. He said, look, it's not magic, it's science. You don't do magic, it's science. So I'd bring one of his favorite textbooks, just get us a good working definition. What do we mean by the difference between magic and science before we get started? Here it is. So the magic, we're trying to hide things, we're trying to confuse people, we're trying to obfuscate. With science, we're trying to explain the natural world, how things actually work. Is that magic or science? That's magic. I'm not going to explain that. But I will try to explain most of the stuff that I do at least a little bit, give you enough information. So if you do have questions later, you can email me. Again, they're going to set it up so with Facebook you can send in questions later on, and then we'll try and answer those later. Or you can ask your teachers, or you can go to the library, do some good research on your own. Now, this next demonstration we're going to do is actually, this is kind of a classic. You may have seen it before, you may have heard of it before. There's one thing about this one that I still can't figure out though. For some reason, my colleagues, the folks that I work with, always want to call this one elephant toothpaste. For the life of me, I can't figure out why they give it a silly name like that, but maybe you guys will catch something I'm missing. Anyway, I'm going to add 4 things to my cylinder here. The first thing I'm going to add is some hydrogen peroxide. You guys probably have some hydrogen peroxide in your medicine cabinet at home. So I want you to think about why you have hydrogen peroxide in your medicine cabinet at home. Now, what you have in your medicine cabinet is about 3% hydrogen peroxide. This is 30% hydrogen peroxide, so it's 10 times as concentrated, but it's the same compound. Now, the next thing I'm going to add is some dish soap, which has nothing at all to do with the reaction, but it is going to help us observe the reaction better. Let's see what I mean by that in a minute. Now, be careful here. You've got to add exactly that much. Good. Kids show, one fart joke. Got to do it. All right. Now, the next thing I'm going to add is some food coloring, which also has nothing to do with the reaction. But it makes it pretty. Another reason your science can't be pretty. A little bit of blue, a little bit of red. Now, after I add the food coloring, the last thing we're going to add is some potassium iodide. Now, you and I don't have potassium iodide in our bodies per se, but what we do have is an enzyme called catalase. And when hydrogen peroxide runs into that enzyme in our blood, it does basically the same thing as when it runs into potassium iodide, which is this. Now, why would they call that elephant toothpaste? Looks like toothpaste. That's why I got to use the red and the blue food coloring to kind of enhance that a little bit. Now, steaming and going on. So next question is, so back to our question about hydrogen peroxide. Why do we have hydrogen peroxide in our medicine cabinet? Well, we put it on cuts, we put it on scrapes, we put it on boo-boos to keep from getting infected. Hydrogen peroxide breaks down into pure oxygen gas. That's what all these bubbles are, is that pure oxygen gas forming. That's a really bad environment for bacteria to grow in. So next time you get a cut or a scrape, or better yet, I hope you don't get a cut or a scrape. Next time somebody knows cooking steak or hamburger, some kind of raw meat, if it's still really fresh, it'll still have that active enzyme in it. So you put a small piece of that raw meat, like a Dixie cup or something, and pour some fresh hydrogen peroxide on it, you can observe the oxygen bubbles forming on the surface. Now, it won't be all big and foamy like this, because you don't have all the soap and everything. But again, you can directly observe, that biological process. And we'll let that keep oozing for a bit. Now, one of the things that most people like about our presentation is that we blow things up. Making my cameraman nervous. Okay, we'll do that. So, now the reason I can do that gag is because this cannon doesn't actually shoot anything out of the end. It just makes a big noise. Now, the adults, the teachers in the room might be terrified to know they used to sell this thing as a children's toy. There's about a 6-year-old kid on a box going, because it doesn't actually shoot anything out of the end. If you've ever known or been a 6-year-old, how long do you think it takes to figure out how to make it shoot something out of the end? Usually their little sibling's doll's head or something. You don't let the kids play with it. What we use it for with the college students is to teach the components of combustion of fire. There are 3 things you gotta have for fire. You gotta have heat, you gotta have fuel, you gotta have oxygen. So, where are we gonna get the oxygen from? Here all around us. For the heat, we have a lovely little sparking mechanism here. Now, in the ammunition box, I'm going to place some calcium carbide. Now, calcium carbide, not a fuel. Calcium carbide will not burn. Now, in the cannon, I got some water. Water is not a fuel. Water does not burn. Okay, a couple rivers in Ohio, but that's a completely different story. Now, calcium carbide reacts with water to make acetylene gas. That's what we use in blowtorches. That burns pretty darn good. So what I'm going to do, I'm going to load it, I'm going to count to 5, then I'm going to fire it on. So, 1, 2, 3, 4, 7, 5. Hopefully security won't show up. All right. Now, you've actually seen this before. If you've ever seen like old-fashioned black and white photographs of coal miners down on the ground, they got that lamp on their forehead. The way that worked was they'd load the mechanism with calcium carbide pellets, the mechanism would drip water on it and generate acetylene gas. The faster you drip water, the faster you generate the acetylene gas, the brighter the flame will be. Now, this demonstration reminds me of another demonstration, especially around this time of year. It's getting close to the holidays, Halloween, Thanksgiving, Christmas. And we sort of want to sort of decorate for the holidays and things. And I'm kind of trying to find sort of more efficient ways to do that for my family. So one of the things I'd like to do is carve pumpkins, but again, it takes time, it's not very efficient. So I'm kind of coming up with a chemistry way of doing that. So I did have to take the guts out first. Got a little bit of water in here. I'm going to put some calcium carbide in here. Gotta make sure everything's lined up correctly first. All right. And then we can carve a pumpkin. Yeah, not bad. We'll let him keep an eye on you guys. All right. Now, this next demonstration, again, in the prep for the show and the advertising thing, they talked about weird polymers and things like that. We've got a lot of demonstrations that we usually do with polymers. Again, our presentation day is about a 45-minute presentation. Usually we have about an hour and a half presentation. So this is kind of the trimmed down version. I want to do at least one polymer demonstration for you guys. This is kind of a favorite for a lot of people. Everybody loves this demonstration when I tell them what it's called. I always like to call this one everlasting ice cream. Of course, it's everlasting because you can't eat it. No, can't have everything. Anyway, I'm going to mix 2 different monomer solutions into my little solo cup here. Now, monomers are the individual teeny tiny molecules that put together end to end to end to end to make the big long chains of molecules that we call polymers. This particular polymer has 2 different chain links, 2 different monomers, so I'm going to add 2 different solutions. Now, while I'm setting this up, let me do a little bit of advertising. Unfortunately, this year, our chemistry open house got canceled because of current events. But again, normally the second or third Saturday in every October, we have our chemistry open house. And so in addition to watching demonstrations be done, you can come and do and make dozens and dozens of things yourself. And one of the things you can come and make is you can make your own everlasting ice cream. So hopefully next year, we'll see some of you come out to our open house and you can make your own everlasting ice cream. Now, I'm happy for some nice strawberry ice cream, so I'm going to put some red food coloring in. But if you come out to the chemistry open house, you can make your own. You get whatever flavor you want. You know, purple for grape, blue for blueberry, whatever. I'm going to make some nice strawberry ice cream. So while I'm mixing the two monomers together here in my cup, there's actually two different reactions happening in here. One of the reactions, like I said, is that the monomers, the small molecules, are working together end to end to end to end to make those big long chains. The other reaction is one of those two monomers also reacts with moisture in the air to make bubbles. Who cares? Well, have any of you guys ever made homemade bread before? Watched somebody make homemade bread? How do you make homemade bread? You mix the yeast, the sugar, the water, the flour, you beat on it, you pound on it, you pound on it, you beat on it, you beat on it, you pound on it, you beat on it, you pound on it some more. You let it set in the corner and rise, because the yeast makes bubbles, the dough traps the bubbles, so the bread rises. And so the same thing here, the polymer is going to trap those bubbles as they form. This will expand to a nice, lovely ice cream milkshake. I always tell students, if you come out to the chemistry open house and make your own everlasting ice cream, you could make a nice, pretty ice cream milkshake. Or you could be a little more creative and make a lovely ice cream spill. Because if you make a really good ice cream spill, then what you can do is take that home, put it on your mom's brand new carpeting, and run! Because she's not going to know it's not stuck to the carpeting till after she kills you. But it won't be stuck, so you pick it up and go, look, Mom, don't kill me, it's not stuck. Run anyway. She won't be listening at that point. All right, it's still pretty ooey and gooey, but about 5-10 minutes, it'll be nice and hard and solid. We'll try and come back later and visit that and see how it turned out. This actually has some important practical applications. If you've got an old house in Texas especially, you've got basically two choices if you want to insulate your house. You can either rip the walls off and put an old-fashioned padded insulation, or you can just drill a few holes and inject this stuff in. And it expands and fills in all the little nooks and crannies. You just spray it in the attic and it insulates the ceiling and all. One problem though, notice it's expanding. You gotta be careful. You put too much in, it just kind of comes out all the cracks and holes and everything. But if you do it right, makes all those itty bitty bubbles make excellent insulation. All right. Now, this next demonstration, you may or may not have seen the demonstration before. There's a pretty good chance that most of y'all have at least seen the results of this demonstration. If you've ever been to an antique store, or maybe if someone in your family collects like old antique furniture or ladies' vanity sets or anything with an old antique mirror. I guess picture what old antique mirrors look like. Well, I'm kind of setting this one up. So while you're picturing old antique mirrors, I'm going to mix 3 solutions in my flask here. Now, okay, so I put gloves on for this one. I'll explain why this one requires gloves in just a second. Now, the first thing I'm adding is just a sugar solution. So that's not a problem. That's not going to start anything yet. Now, the second thing I'm going to add is a silver nitrate solution. Now, this is the reason why I have to wear the gloves. If any of y'all know anything about old-fashioned black and white photography, you might remember they use various silver salts for developing black and white photographs. Silver bromide, silver nitrate. This is silver nitrate. If I get any of this on my skin, nothing will happen. Until I walk outside. As soon as the sunlight hits it, wherever I got it on my skin will develop like an old black and white photograph and turn kind of blackish, brownish, orangish, purplish for about a week and a half until the skin wears off. My wife prefers that I wear the gloves. And we add it, nothing happens. Now the last thing I'm going to add to our flask is a base catalyst. Now a catalyst is what chemists call a reagent that doesn't get used up in a reaction, but it does make the reaction go faster. So I kind of have to be ready to go before I add the catalyst. So I'm going to get the cap on the bottle, grab the stopper, grab the paper towel, then we can get to adding the catalyst. Now once I get the stopper on, we can finally get back to my original question about old antique mirrors. So do old antique mirrors look the same as brand new mirrors? What starts to happen to mirrors as they get older? They kind of get cloudy or foggy. They get tarnished. Well, the way they used to make mirrors, they still make some mirrors this way, is they'd take a sheet of glass and clean it off really, really well, and they would plate the back of it with silver metal. And they would paint over that silver metal with tar or paint or shellac or something to keep the oxygen in the air from getting in and tarnishing the silver, turning the shiny silver metal to black silver oxide. Well, over time, eventually things get through that tar or paint or whatever, and it oxidizes the silver anyway. You may also see this around Christmas time. You can see the really nice expensive German or Spanish or Czech Christmas tree ornaments that are silvered on the inside. Basically, we're making a giant Christmas tree bulb. I hate that. The worst thing about this whole demonstration is I have to sit here looking at my own hideous face. Can you guys see my face in the mirror? Hi, how you doing? Not bad. Our glass blower, Bill Merkin, did that. He did a nice job. So the face was there the whole time. We just couldn't see it till we silver plated it. Now, it's really, really valuable. Now that I've silver plated it, yeah, not so much. Only a few molecules thick of silver, not very much silver at all. The flask is actually worth a lot more than the silver is. So when you get done here, I'll take it back to the lab, wash it out with concentrated nitric acid, have a nice clean flask to do it again next time for some more folks. But for right now, we'll let Herbie keep an eye on you guys. Now, the next demonstration we're going to do is one of my favorite ones. This one's called the Briggs-Rauscher oscillating reaction. You guys know what oscillating means? Back and forth and back and forth and back and forth and back and forth. What does oscillating mean? Back and forth and back and forth and back and forth. What does oscillating mean? I can do this all day. No, I'm not going to do that to you guys. So again, the idea of a reaction that oscillates. So this is called the Briggs-Rauscher oscillating reaction. I got to do a little bit of a pre-apology on this one. This reaction is, how shall we say, finicky, and we're doing it outside today. So we're going to hopefully get it to work, but sometimes it's a little bit sketchy. The good news is, even if the reaction doesn't work, we get a nice little magnetic stir plate here, so if nothing else happens, we get a nice little tornado in a jar, which is always fun. But hopefully the reaction is going to work for us. So I'm going to add 3 solutions to the flask. Add the first one, nothing's going to happen. Now, for you guys to get the full impact of this demonstration, it's important that you notice, as the second solution is being added, we observe that nothing happens. Old teacher trick, just reeling them in, reeling them in. Anyway, now before you add the third solution, let's see if we can get that tornado flying just a little bit. Whee! I don't want to go quite that fast. We're going to slow that down just a little bit. All right, now we have the third solution. Turns out this reaction doesn't really like to be colorless. We much prefer to be sort of a nice, warm, golden color. But you know what? It doesn't like gold either. It must be blue. It doesn't like blue either. It's kind of fickle. What it really wants to be is colorless. Good. Color. Gold. Gold's a good term. Blue. And it's going to keep doing it. It's warm out here, so the reaction's going a lot faster. A little bit of a side note. General principle in chemistry. For every 10 degrees you heat up a reaction, it doubles the rate of the reaction. So this is going about twice as fast as I'm used to it going. But still going, at least that's good. So, again, there's 2 reasons why I especially like this reaction. Number 1, as much as I love Texas A&M, I do love Texas A&M. They've been wonderful to me for decades. But I graduated from the University of Michigan. Remember what the colors are for the University of Michigan? Blue and gold! Oh well. The other reason is, think about what's happening here. The product of the first reaction is a reactant for the second reaction. The product of the second reaction is a reactant for the third reaction. The product of the third reaction is a reactant for the first reaction. It keeps going in a cycle like that. This is incredibly unusual in a chemistry lab. I've only been able to find about 3 or 4 reactions that do this. Most of them don't even change color. You have to have like an electrode to see the resistance change or something. But you know what? This happens all the time. Inside you and inside me. Our bodies are designed so they don't waste things. You make too much of one thing, your body converts to something else. You make too much of that, your body converts to something else. So for the older students or for the teachers, if you've had a good biology class or biochemistry class, you've learned about, the younger students will learn about things like the Krebs cycle, the citric acid cycle, the glucose cycle inside our own little teeny tiny cells that recycle and recycle and recycle. And this is a good demonstration to demonstrate that concept visually for students. Now it should go through a few more iterations. I'm going to start working on the next couple of demonstrations. You can kind of keep an eye on it in the background as we're going. All right. Now, this next demonstration, we're going to pull out a little bit of dry ice. I'm kind of running short on room here. I'll put it over here. Now, stuck. There we go. Should you ever hold dry ice in your bare hands? No, not unless you're an idiot or well-trained, one of the two. I've been doing this for a few years. It is minus 78 degrees Celsius. It will give you frostbite if you're not careful, but notice I'm moving it around in my hands pretty quickly so it doesn't come into close contact with my skin. Now to help us, we call it dry ice because remember it goes from it's sublimed. It goes from a solid directly to a gas. It doesn't go through that liquid phase in the middle. Now we're used to seeing, what we usually use dry ice for, especially around Halloween and things, is to sort of make bubbling cauldrons and things, so we can see it sort of bubbling through the water, and that is a physical change. We're seeing the solid carbon dioxide turn into gaseous carbon dioxide, but it's still carbon dioxide. For this demonstration, we're going to want to do a chemical change as well, though. So carbon dioxide reacts with water to make carbonic acid. That's one reason why we use things like carbonated sodas have that sort of tart, acidic flavor, is because of the carbon dioxide reacting and making carbonic acid. So to demonstrate that, what I'm going to do is I'm going to take a little bit of sodium hydroxide. Grandparents probably called it lye, like for making lye soap. But chemists call it sodium hydroxide. A nice basic solution there. And I'm going to add some universal indicator. I'm going to call it a universal indicator because instead of just doing one color change like most acid-base indicators does, it actually goes through a whole series of color changes. So based on the color, we can tell approximately how acidic or how basic the solution is. So you can see under neutral conditions, it's kind of a greenish color, but under basic conditions, it turns a really lovely shade of purple. Now, we're going to add some more dry ice, and as that bubbles through, the dry ice will make carbonic acid. The carbonic acid will neutralize the base, and as it neutralizes the base, the indicator will indicate that process by changing from purple to blue to green to yellow. It's got really acidic to turn red, but it's not going to get that acidic. Now, there is kind of a home version of this one that you can do. Let's watch the colors change first, then we'll talk about the home version. It's starting to change color. We've got kind of a purplish blue. We're starting to get to a darker blue. I added just a little bit too much base this time, so it's taking a little bit more time. There we go. We got a nice sort of bluish going. Shifting from blue to kind of a little bit aquamarine. Eventually to sort of a dark green. And then it'll shift slowly from a yellowish green into a nice bright yellow. So for the home version of this, what you guys can do is you can talk your parents into buying you a nice head of red cabbage. Because we all like to eat red cabbage. You don't have to eat the red cabbage. You don't have to cook the red cabbage. Take a couple of these of that raw red cabbage, chop them up or tear them up real small, put them in a Ziploc bag, add a couple of cups of cold water, Ziploc it shut, let it sit for a couple hours. Go read a book, go have dinner with your family, go play with your friends. When you come back, that purple cabbage juice that you extracted is a universal indicator. And you can pour that in a few clear Dixie cups and test things around the house, like lemon juice, pickle juice, antacid tablets. You can turn that purple cabbage juice pink and blue and yellow and bright green. Now, I always have to be careful to do a warning at this point. Never just randomly mix chemicals around the house. You can kill yourself that way. But if you're mixing things you would normally eat anyway, like lemons and pickles and cabbage, stuff you'd eat, pretty safe to play around. All right, if you'd like instructions for that, if you go to our webpage, we actually have it's mostly a scheduling mechanism, but we do have some instructions for some demonstrations, or if you just Google red cabbage indicator experiment, you can find a few different variations there. So while this one's bubbling through, I'm going to start another demonstration that's kind of related to this one, and then we'll see if we can tie them together. So I've got an empty 2-liter soda bottle. I'm going to take some of that same 6 normal sodium hydroxide solution, about 35 milliliters, and I'm going to add that to our empty soda bottle. And I'm going to ask you guys to help me out. scientists and make some observations. Okay, so I'm going to go outside for a soda bottle, get the cap on, good and tight. And then you guys let me know if anything interesting happens. Well, I can't hear you now. I'm assuming that you're responding out there. So what's happening? It's shrinking, it's collapsing, it's smushing. Now usually when I do this demonstration for itty bitty kids, somebody will go, ooh, the air's leaking out. Is the air leaking out? No. So I put the cap on real tight, so you know the air's not leaking out. So the next obvious question is, do you think it was really an empty soda bottle? But we didn't see anything inside before I put the solution in there. So part of what we're supposed to learn from this demonstration is, just because we don't see something, that doesn't prove that there's not something there. Before you guys got here, I filled the bottle with carbon dioxide gas. So I added the base, carbon dioxide dissolves in water, reacts with the base, and so it keeps neutralizing and neutralizing the base, so it keeps pulling more and more of the carbon dioxide out of the atmosphere in the bottle, and that creates a vacuum. So if I create a vacuum inside the bottle, the air pressure on the outside, give me this lovely table ornament, modern sculpture. Now, one of the particularly nice things about doing this demonstration right after that demonstration is that we can use it to restart the colorful soda. As we go back to the basic conditions, we go back to the basic color. Now, if we've got enough dry ice in there, I think we do, should go back to that whole series of color changes again, from purple to blue to green to yellow. I'll let you guys keep an eye on it and see how far it actually goes. All right. Now, this next demonstration, I gotta admit, this is my absolute favorite demonstration to do while I'm on the road. This one is called Rainbow Magic. Now, the idea is I have a pitcher of water and I have a box full of little beakers. Now, if this works out right, what should happen, as I add the water from the one pitcher to the 6 little beakers, I should get all 6 colors of the rainbow in order. So I want you to kind of virtually play along with me. And I'm going to ask you to help me out and give me what are the 6 colors of the rainbow. We got red, orange, yellow, green, blue, and purple or indigo or violet, whatever your teacher called it. I'm going to call it purple today, okay? So, now before we do this one, I do want to take a brief pause and thank Dr. Shirley Hammond. She's off camera here, but she was the person responsible here for getting everything set up. And so one, I want to acknowledge her for all that hard work, but above and beyond everything else she did. Of all the demonstrations I do, this is the hardest one to set up. It's very precise, very delicate, and I was just afraid I was going to run out of time and not get to do this one for y'all. But Dr. Hammond was she stepped up to the plate, she volunteered to set this one up, so I want to make sure and give her credit, because if it doesn't work, it's her fault. Just kidding. Now, all right, so what were the colors again? We got red, orange, yellow, green, blue, and purple. Good. So, red. It's okay, everyone, small, 1 or 2 more. Orange. Yellow. Now, I know for a fact that Dr. Hammond's a much better chemist than this. Maybe she didn't mess it up. Maybe I'm messing something up. Do you see anything happening? I know, she didn't mess it up, I'm messing it up. Not adding enough. Red, orange, yellow, green, blue, and purple. All right, virtually results of our Now, you guys have done enough experiments, enough products, enough, things like that to know whenever you do something big and messy like this, you haven't finished until you clean up. All right, so red, orange, yellow, green, blue, and purple. And now it's done. What just happened? Well, remember we're doing acids and bases and indicators. So each one of the beakers had its own indicator or a combination of indicators. and a little bit of acid. So I only added a little bit of base. It wasn't enough to neutralize the acids. The indicators didn't change color. But once we added enough base to neutralize the acid, then the indicators indicated that by changing colors. All right then. Why did it all go back to clear when we just slushed everything back together again? If you're watching carefully, you saw the sneaky little beaker back here that had acid in it. And while I was talking, I poured that in. That was enough acid to neutralize the base, and so when the solution turned back to basic, the indicators turned back to clear. So a little bit of a trick, but good science behind it. Acids, bases, indicators, pretty colors. I like that demonstration. All right, let me move this out of the way. Now I can pretty much guarantee you that the next set of demonstrations we're going to do are going to be the coolest thing you see all day today. They might not be the most interesting, probably not the most important, but definitely the coolest thing we're going to see all day today. So we're going to try and have a little bit of fun with liquid nitrogen. Now liquid nitrogen boils at minus 321 degrees Fahrenheit. Definitely the coolest thing we're going to see all day today. Now, whenever I get out with liquid nitrogen, I always like to use that opportunity to introduce my friends and my audience to a very important person. And that person is our Chemistry Roadshow mascot. Now, our mascot is Nitro the Dragon. He's a very interesting little dragon because he's not your run-of-the-mill, fire-breathing dragon. He's a liquid nitrogen-breathing dragon. Now, he's a little tiny guy. He's kind of shy. He always tries to hide. Oh, there he is. Isn't he cute? He's vicious. It's kind of fun to have on a hot summer day, though. It'll blow nice cold air at you. Whee! Wow! Excuse him. Breakfast burritos. Now, is his tail hard like that when you put it in there? I don't think so. I don't know. I have to think about that. Now, this next demonstration, if you've ever seen any demonstrations at all with liquid nitrogen, you've seen this one, but it's too much fun not to do. So, if I were to take, let me just transfer my liquid nitrogen to this other reservoir. If I were to take a flower and I were to stick it into the liquid nitrogen, at minus 321 degrees, what's going to happen to our flower? It's going to freeze, right? What are flowers mostly made out of? Water. Just like all living things, they're mostly made out of water. So we can predict with a high degree of certainty that our flower will in fact freeze. Not bad. Let's try that once more in slow motion. Now I can tell when our flower is frozen, because as long as liquid nitrogen is freezing the flower, as long as it's absorbing the heat from the flower, it boils pretty vigorously. Once it's absorbed all the heat, once the flower is completely frozen, then it just kind of goes back to simmering for the air temperature around it. So we usually like to use carnations for this instead of roses. They have a lower water content, they freeze faster. I don't have to spend as much time pretending that I'm saying something while I'm waiting for it to freeze. Flower chips, nice. All right, so let's see. So we did nitro, we did the flowers. Ooh. I wonder what would happen if we stuck a balloon in the liquid nitrogen. What might happen? It might pop, right? I hate it when they pop. I'm sure you guys want me to do this. All right. Ah! Okay, didn't pop. Anybody notice anything happening? Shrinking, yeah. It says the air inside gets colder and colder. Molecules in the air move slower and slower. And eventually they'll condense down to a little puddle of liquid air at the bottom. Now, Dr. Hogg used to have a joke about this. He said, you know what? this would actually solve an interesting problem. Let's say you had a friend who had a birthday coming up, and you want to show them how much you like it. So you went, I'm going to buy a whole bunch of balloons to decorate for the birthday party. The problem is, when you got to the store to pick up the balloons you ordered, they had done you a favor. Well now, and they had blown up the balloons. Well now they won't fit in your car. Well, Dr. Hogg said, that's okay. All you got to do is fill your trunk with liquid nitrogen. His joke, not mine. Sometimes people laugh. Sometimes they don't. So the first question was, what happens when we put the balloons in the liquid nitrogen? What's the next obvious question? What happens when we take them out? It's alive! Actually, that once per show is a mad scientist contract. Now I do two because they get a kink in them, they might pop. So if they get twisted, they might pop. But as long as they don't get a kink in them, they should expand back to the same size. Because for all the high school students and the teachers, your PV equals nRT. Same quantity of gas, same temperature, should take up the same volume. Sometimes you have to give a little kinetic energy. Ah! There we go. That one off. I got one. Good. All right. Now, while we got the liquid nitrogen out, I always like to, again, use it as an opportunity to do a little bit of what I like to call public relations or damage control. Again, one of our goals in doing the roadshow is we like to encourage students to consider the possibility of scientific career fields. Again, we understand not every student necessarily wants to go into a career in science, and that's fine. We hope each student has a career path that's especially interesting, especially meaningful, especially enjoyable for them. But we would like all the students, no matter what they do for their job, to at least enjoy science, appreciate science. Heck, at least not be afraid of science. On the other hand, we do hope we can motivate some of the students we interact with to consider the possibility. Maybe they would like a career in a scientific field, chemistry, physics, biology, engineering, things like that. But it's important to me, at least, that I be very honest with you. If you do go into a career in science, you will get a reputation for being a dork. Just honestly, you will. So to prove how manly I can be, should I stick my hand in the liquid nitrogen? There's always like 3 kids in the front row going, yeah! So for you guys, I'll do it. Smoking jacket. So, does that prove how muy macho I am? No. My wife thinks so, but she kind of likes me. Now, did I just stick my hand in and hold it? No, in, out, fast. You've seen this before. It's called the Leidenfrost effect. You ever seen an old Western movie? There's a blacksmith. He's got a red, hot horseshoe. He pounds on the horseshoe. He pounds on the horseshoe. Takes the red, hot horseshoe, tosses in a cold bucket of water. What happens? Instantly boils the water. Remember, minus 321 degrees. Compared to the liquid nitrogen, my hand, your hand, is like a red hot horseshoe. It instantly boils the liquid nitrogen, creates a vapor layer around my hand that protects it. The liquid nitrogen never touched my hand. But if all these guys around here had come up here and held my hand in the liquid nitrogen, well, I was kicking and screaming, because I would have been kicking and screaming. What would eventually happen when I finally pulled my hand out of the liquid nitrogen? I would have frozen solid and shattered just like the flowers, because I'm mostly made out of water too. But in, out, fast. You've also seen the Leidenfrost effect before if you've ever been holding out in the kitchen. And a hot frying pan. If you drip cold water on a hot frying pan, does it immediately hit the frying pan? Kind of skitters around on its own steam. That's another example of that Leidenfrost effect. All right. Now, these last 2 demonstrations that we're going to do, I'm hoping are going to work well for us. Part of the issue we're going to have is we're outside, so we've got a lot of ambient light, and these are ones that are best done in the dark. But I wanted to do at least a couple of our fire and light demonstrations for y'all, at least to give it a shot. So this first demonstration is called Elemental Colors. And the idea is, if you've ever studied anything about the stars, the planets, the solar system, either for school, or maybe you're just interested in that sort of thing, or maybe you've seen a movie about it or something, you've heard things, you've been told things, you've read things like the sun is made out of a certain amount of hydrogen, a certain amount of helium, a certain amount of iron, a few other elements. Well, there's a natural question that any good thinking student ought to have when they're told something like that, and that is, how do they know I mean, it's not like you can go to the sun and pick up a sample. Well, it turns out when you heat different elements and different molecules up, they give off different characteristic frequencies of light. And so based on those characteristic frequencies, they can tell what those distant planets and stars and things are made out of. And if those frequencies happen to be in the visible range of light, that means they give off different colors. So to demonstrate that, what I have here are 6 different metal salts. I'm going to add some methanol for fuel. We have potassium chloride, indium chloride, copper chloride, sodium chloride, strontium chloride, and lithium chloride. Now, for safety reasons, I'm going to put fuel way back here. Now, I'm going to take a match, and again, we'll see how the lighting goes. But at first, you might just see the blue from the methanol running. But as the salts heat up, so I'm going to do the Rube Goldberg thing and light the match with my lighter. As the salts heat up, what you should see is the characteristic colors for each of those metals. You should see violet for potassium, blue for indium, green for copper, yellow for sodium, orange for strontium, and a nice bright cherry red for lithium. Now I can see the violet a little bit. The green and the yellow and the orange are starting to flicker in. And again, as they heat up, those colors should become more intense. And hopefully there'll get enough contrast in the video that you can see that. Now you've actually observed this phenomenon before. If you got a gas stove at home, what color is the flame on your gas stove? That's going to be blue. But if you go camping, you know, it's wood fire, maybe charcoal fire, try and remember what color that is. That burns sort of a nice, bright, sort of orangish yellow color like this one, the sodium one. Because wood has a fair amount of sodium in it, so it burns that characteristic sodium color. Now, while those are heating up and hopefully becoming more intense, I'm going to start another demonstration and see if we can tie the two together. Now this one actually has some important applications for things like fire safety and firefighting and things like that. This one is called the fire tornado. Now the idea is, if you're a firefighter fighting a forest fire, try and say that 5 times fast. If you're a firefighter fighting a forest fire, a lot of times that fire will start off just as a little tiny fire down at the base of the trees. The problem is, if the wind rips up just right, or just wrong, that little tiny fire can get whipped into a vortex that quickly becomes a fire tornado. That becomes a much more difficult fire to put out because that can catch the top of the trees, the canopy of the forest on fire, and the fire spreads rapidly over the firefighter's head so they can't really get to it. If you've been keeping an eye on the California wildfires and things, I've seen some pretty spectacular images of fire tornadoes that kind of started in the middle of those fires as well. This is a nice, small, contained one, though. We've actually observed a similar phenomenon to this before, only upside down. If you've ever taken an empty 2-liter soda bottle and filled it with water, turned it upside down and spun it around, try and remember, does the water come out faster or slower when you spin that around? It comes out faster, because you're creating a hole in the center that gives the air a straight path into the bottle without bumping into the water, and the water can come out along the edges without bumping into the air. So this, again, similar concept. We've got a column of hot air that can rise quickly straight up. So as it rises, it sucks in, draws in fresh air and more oxygen to feed the flame. So I'm going to put our one big fire dish out, and I'm going to replace that with a slightly modified fire dish. Now, I said before that all of our specialized glassware was made by our glassblower builder. All of our specialized metalwork was done in our machinist shop by Will Seward and his team. I really like working with those guys. Really creative, really smart. If you're interested in a career where you're doing math and science, but also sort of creating and building things with your hands, things like machinist, things like glassblower are some cool things to consider. So what Will did for me here was he took that big metal fire dish and he divided it into 4 smaller compartments for me. And so we're going to get a smaller fire tornado. What will hopefully be interesting is in each one of those compartments we have one of our metal salts. So what we should get is a nice, so 2 of them have lithium chloride, remember that's the cherry red one. 2 of them have copper chloride, that's the green one. So what we should get is a nice red and green candy striped fire tornado. And it may take a second to do that. So we'll give it some time. I can see the red. I don't know if you guys can see it or not. I'll try and stand over to the side because the lab coat might actually interfere with the colors. I'm not for sure. You start to see that the green sometimes takes a little bit longer to come in. started with you guys. There's some green. Almost to the point where it's being good colors. Now I'm seeing some red better. There we go. Alright, there's some nice red and green, candy stripes, white or stripes. And that will wrap it up for today. Thank you guys for showing up. We really appreciate it. Again, thanks to the Foundation, the library for inviting us and for making this possible. Again, if you're interested in having us come out to your location, please email me. If you just Google Texas A&M Chemistry Roadshow, we're the first thing that pops up. Thank you very much. Have a great day, guys.